so it's recording now. Volume's on, so recording, microphone's on, share screen. All right, so here we have the next one, which is the naive Bayes algorithm. So I'm going to create a new file, Python 3. I'm going to save it as, this is going to be naive Bayes, right? So I'm going to call it naive Bayes, right? This will be your module for that, naive Bayes. Hit save. Okay, so here we are. And now we are ready to proceed. So you guys should remember from last week, right? Hopefully you remember from last week that I went over the lecture and I described how the naive Bayes algorithm kind of works, right? So it's basically a probabilistic type of an algorithm, but I gave you the intuition, so I'm not going to discuss all of that really again. Instead, today we're going to try to implement the algorithm. As usual, I will give you the majority of the code, but I do want you to kind of bring it in that final part of it. Make sense of it. Okay. This naive Bayes homework will be due about 2 weeks from today, so I'm not gonna cover. This will be the last ML algorithm, for classification for a while, given that the next topic after the exam will revolve around features, right? So it'll revolve around feature ranking, and also it'll revolve around, so we'll look at a couple of things there. I may not assign a homework for that, but we will do then singular value decomposition, and in particular recommender systems. So you can expect that the next assignment will be a recommender system. After that, the next assignment would probably be the next assignment would be the reinforcement learning, and then that'll take us to the final really things, which are neural nets and unsupervised HMM and all that. All right, so today then, as I said, we are going to go over the naive Bayes algorithm, okay, or naive Bayes code. As you can see, this code is actually, it'll be very short, which is pretty interesting, but it is a little bit more complicated, but don't worry too much about that. I'll explain a lot of the reasons, but it really, ultimately, we need to go back to that equation, right? So if you remember, let me open up the whiteboard. We had an equation last week, right? And we are going to sort of go back to that. So if I open, let's see, I can actually just open Brightspace, right? Don't have to write it. So if we go back to Brightspace here, under naive Bayes, we had our naive Bayes PDF from last week. And this is what we need to use, right? So this is what we need to use now to kind of derive our algorithm, right? So you guys went over this whole intuition, right? If you don't remember, just go back to the code. We kind of started here, right, with that formula. And we're just going to make a modification to this formula a little bit. Remember that, we kind of arrived at this. We talked about the simplification. And ultimately, we could get rid of the denominator, and we arrived at this function, right? So the probability of a document given C, which became probabilities of the features themselves, right? And then ultimately, this became a multiplication, right? So this equation here is really what we were looking at. However, as it turns out, there is, before I say that, so once we have this, then I gave you these, the fact that we need to know what these parameters are, right? We talked about that, what are this one and this one. And so that's what we have here. And we define them as this. This is this formula. And for this one, it's this formula. However, this formula we're going to keep as is. We're just going to look at it from a frequency point of view. However, this formula we're going to tweak a little bit. Okay, so we're going to tweak a little bit this formula just to kind of, although we could have used this formula and it would have worked, we're going to assume that most data that you get, because we want to generalize this algorithm now to beyond documents. You know, we want to use it with iris, with everything. So we're going to assume that a lot of the data in the world comes from a normal distribution. Okay, so that will be the assumption that we're going to make. So if you remember, that just means using the Gaussian equation or the bell curve, right? So we're going to tweak our data to fit within this. And part of your homework, the hardest part probably, will just be figuring this out. I'll give you some of the intuition for it, but I'll give you most of the code. All I'm saying is, like, this part is really the only thing that we're going to modify. This simple frequency that we had here, we're going to change to instead have the data follow a normal distribution. But at the end of the day, it's still kind of a probability from 0 to 1. The other thing we're going to deal with, if you remember last week, I said, well, what about the fact when the values are zeros? Well, they're just add a 1, and that's, you know, that takes care of the problem, right? It's a multiplication times 1. However, that in itself can still have problems because sometimes the values can be very tiny. Like the more you, if you've ever thought about multiplying 0.05 times 0.02, what do you get? 0.05 times 0.02, what do you get? You get 0.001. Now multiply that times 0.001, and what do you get? 0.000001. Do you see that? So the problem with that is that the numbers start to become very tiny, right? So you multiply, let's say, 0.001 times 0.001. So if I do this, those are already tiny, right? If you look in my whiteboard, but the result of this is actually 0.00001. It's got 5 zeros. So it's starting to become so small that, as you know, computers will have a problem with that. You know, that's a numerical method's kind of a problem. So there's basically something that we can do. Now, you know that we are trying to calculate these probabilities, right? Multiply them like this. However, what we can do is there is a kind of a, let's just, without getting into too much detail, let's just think of it as a rule in math that says that if we have a situation like this, we can simplify it by doing log of the probabilities and just add them. And that is basically equivalent for our purposes, okay? So instead of multiplying, we're gonna add, but instead of using the actual value, we're gonna take that value and run it through a log function. And a log function is just like a mapping function. So if we have very tiny values, now they get converted into, like, you know, bigger values. So we take care of those problems, okay? But in terms of comparing the probabilities, everything will still work the same. Does that make sense, guys?
Yeah.
Okay, great. So that, you know, that's just the idea. So sometimes when you know, a lot of optimization and a lot of, like, numerical methods, applied math, a lot of the time it's just using little tricks like this, right? Little tricks like this still provide excellent results, and they improve performance, and the computer doesn't, like, you know, die, right? You don't want to get this NaN. You guys know what that means, NaN?
Isn't it like a non-real number or something?
Yeah, not a number, right? So you,
Yeah.
computers don't want, don't want to fail. You know, you don't want to end up, imagine if you have tons of features, this number could be gigantically small. And so at some point your float, you know, those floats regardless of whether it's float 32, float 64, they can handle it, right? And so we have to take things. So that's why, you know, the numerical methods and those techniques allow you to take things that are pure math like this and just make it more practical from a computational point of view. Okay, and so that's, you know, it's pretty straightforward, right? Run it through a log function and add it. That's it. And, you know, NumPy will provide all the tools that we need. That's one of the things that we're going to change. The other thing we're going to change is we are going to go, if I go back to your PDF, well, we took care of this already, right? And then the other thing is, as I said, so we arrived at this, you know, very nice formula. And if you know this formula, you just do it for every class, right? And you look at probability of C and then this probability. As I said, the probability of C, this one here, we're not going to change. It actually is just still this. But this one, we are going to change a little bit. So the probability of W given C, remember that W were actually the features, right? We're actually the features. So the example I did was representing a document as words. But in this example, because we're trying to now generalize, we are now trying to generalize to features like iris, which iris is not made of words. It's really just measurements of the stem, the you know, and so on. So we want to generalize it, right? So instead of writing the formula as PWCJ, we're just going to say PFCJ, right? So PFCJ. So I'm going to go over here again, back to the Jupyter notebook, or sorry, to the whiteboard, and I'm going to say PFICJ, right? So I'm just generalizing it to be a feature instead of it being a word. Where was it? So, yeah. So, and we just said that this was some kind of a frequency count, but now instead of it being a frequency count, we're going to say actually, because frequency counts would have also given us like numbers, right? So it would have given us a probability between 0 and 1. So it would have given us that, like it would have been, you know, that word in that class, you know, given all the current the circumstance like 0.6 or 0.7, etc. However, we want to actually have a better thing, right? Have a better tool than just looking at frequencies for something that is, you know, plants or images of cats and dogs, you know, all kinds of values. So basically, as you guys probably know, the intuition in the world is, you know, from your statistics class was the Gaussian, right? The Gaussian or the normal distribution. And the normal distribution just says, well, usually events in the world have a mean, right? So they happen, you know, temperature has a mean, right? So usually it's not as extreme as it is. I think next week we're going to get down to -11 or something, right? But that would be where? In the normal distribution, kind of an outlier over here, right? You guys see that? But intuitively, you know, everything is going to be sort of in a mean of, you know, I don't know, 40s, 50s a year, you know, for the year. And so that means there's a mean associated with this, and there's the variance, or what is called a standard deviation. All right, so a little bit later, if we have time today, actually, I'll remind you of these equations again. You know, how do you calculate the mean? How do you calculate the variance? Kind of to motivate that a little bit more, but we're gonna need them, all right? We're gonna need them to be able to calculate the probability of the feature. But now what I'm saying is we're gonna run this through the mechanism of a function called the Gaussian. All right, so instead of just calculating frequencies, now we're gonna plug in that feature given the class into that function, and the function itself will give us the new probability. All right, and the probability is going to be based on the famous you know, Gaussian distribution. all right? So the famous Gaussian distribution. Does that make sense as well, guys? Are there any questions about what we're doing here? And why I'm making, no questions?
Nope.
All right. Yeah, exactly. So good, good. So that's really the idea, is to kind of go over this. So let me just, so we're going to write the code, right? We're going to write the code for this. And so here I have the Gaussian function. So I'm just going to write it for you here. And just remember, the parameters here are going to depend on our features, right? So on our features given the class, so we need to have some kind of a mean, right? And then we're going to have some kind of a variance, right? So those are the parameters associated with this. So the Gaussian function, this is so famous, you can just look it up on Wikipedia, but basically this function looks like this. So it is 1 over standard deviation, 2 pi, and then this is exponential, right? So exponential, and then we're going to say this is 2, you know, and then the x, we calculate this for all x's, and we take the mean difference, basically, right? So that's really the Gaussian equation right there, right? And that's what we're going to do. So we need to calculate for all of our feature data, the mean, the variance. That's going to be, you know, if I change the color here, that's going to be this parameter and this parameter and this parameter. The other parameters are constants, like 1, 2 pi. Exponential just means e to the something, right? So e to the x, right? So then e is just the value itself, and x is basically this whole term here. Okay, and then 2 is a constant. And then, as I said, the mean we calculate, the variance we calculate, and x is going to be all the values. So we have to do some kind of a sum situation, etc. Okay, so now that we have this, what we can do is we can kind of start to take a look at this in the code. Now, for the variance, the mean, I think you guys pretty much know how to calculate the mean. So that should be, as you know, the mean is what? Just the sum, right? So x1, x2, x3 divided by the number of samples. And samples. Right, so for instance, what is the mean of these numbers? Let's say, you know, 6, 11. So these numbers like 6, 11, 7, right? So that's just going to be 6 plus 11 plus 7, that's 24, right? And then divided by 3. So 24 divided by 3 is 8, right? So that's your mean there. We're not doing anything special like the weighted mean or anything like that. We're just calculating a standard mean. Okay? Now the variance I have it here, is another equation. Variance, right? It looks like that. The variance measures how much a list of numbers varies from the mean, right? So first we need to calculate the mean or the average value. So it is frequently used in statistics to measure how large the differences are in a set of numbers, okay? It is calculated by averaging the square difference of every number from the mean. So here is the formula for that as well. So that's going to be 1n, right? And remember, this just means sum from I1 to n. So we're going to sum all those values. And that's going to be then we take xi, which is our sample, and we take the difference and square it, right? Square is so that we can, if we have negative values, right? We have -1, -2, right? We don't take into consideration the symbols. We just get the distance, basically. All right, so this is what we're going to be using to calculate that probability. All right, so if you remember, as I said, we're changing that probability a little bit in here, given that we're going away from numbers, right? So this one here, we're going away from numbers, from just words, sorry, to actual other values that could be numbers like, regular features, measurements, etc. So again, to recap, this function that we defined previously last week, last week we defined the probability of Wi given Cj is now being modified to generalize to all features. And given that we don't just want to use the frequency that we had before, right? If I go back to the PDF, we don't just want to have this frequency like this, right? Because this is more of like with words. So we want to modify that a little bit to be more what the real world distribution is, which usually refers to the normal distribution, right? The normal distribution. So that takes us then to calculate those probabilities. Just like before, we were just counting, the x's given the classes. Now we're still dealing with the f's given the classes, but we just plug them in here into our function, and then our function will look like this, which is the standard Gaussian function, all right, that I just described, right? So I talked about how the parameters that we usually take, are these, right? So standard deviation, right? And so we need to calculate for this then both the mean and the variance, okay? This is the formula for the mean. We're going to implement that in with numpy pretty straightforwardly. We will also need the formula for the variance, which we will calculate quite simply like that, pretty straightforwardly with numpy. And then given that, and we don't even actually have to write this equation, right? Because numpy has methods like mean and variance. So I'm just kind of giving you the idea. And then finally, once we have all the parameters, whenever we want to calculate the probability, we will just run it through this and think of this as an actual function, okay? And part of the homework will really be to kind of wrap up the code that I'm going to give you. So I'm going to give you the code, most of it, and then you will just complete it, okay? As I said, the Gaussian function is the probability density function of the normal curve. And I've given you the formula, and that's pretty much it as far as this idea here. Are there any questions, guys? Does this make sense?
Yeah.
All right. So this is, think of it as the intuition. Again, if you're curious, why are we running it through the Gaussian? Because we want to take into account when we calculate the probabilities that, that's usually the behavior. That Gauss, the famous scientist who figured out, that's a lot of data in the world follows that. You pick a tree, you know, measure it. Well, it turns out, you know, after I do this 100 times, there's a mean, there's a standard deviation. And so it makes sense that now whenever you calculate the probabilities, you kind of calculate them through this equation, okay? Through this equation. All right, so I will post this as a PDF also, just so that you have the formulas there and the intuition where this is coming from. All right, so now that we've discussed this, that's really, you know, those are the only two tweaks that we had to make. This one of the Gaussian variance and mean, and then also to replace this equation that you're looking at over here in the whiteboard, and then also what I said about replacing probability multiplications, which could result in underfavors. And so we can just change them by running a probability through a log function and then adding the values instead of multiplying. Okay, so that will be basically our approach over here. So now that we've discussed that, we are ready. We have some time, so we'll get the code running, started today, and then we'll probably finish it up, you know, next Wednesday, on Wednesday. All right, so now that I've talked about that, you kind of know where I'm going to be coming from. So I'm going to go ahead now and switch to the Jupyter Notebook again. All right, so here we go. You should be seeing the Jupyter Notebook code. And we're just going to go ahead and implement it. As I said, this homework will be due 2 weeks from Wednesday, okay? So that you'll have plenty of time to get it to work. So let's go ahead here. And continue. Let's take a look at Naive. So it should be not very long, 40 or so lines of code, okay? So let's start with the basic tool. So import numpy as np. All right, so we're going to import numpy as np. And you know what do we want? In this one, we need to have two functions plus the Gaussian. So we're going to have, let's just think, define. Oops, let's just make it like this. So define, and the function will be fit, right? Or what did we call it? Train? Train. Remember, I'm not doing this object-oriented right now, but you could easily just make a class for this, and we might do that later. So let's say print. Then I'm going to do another function, define predict, right? What do we call it? Predict? Yeah. And this is only being done for one prediction. So you give it one test sample, it gives you a label, a predicted label. Okay, so I'm going to do print here as well. And then finally, we need the function for the Gaussian, right? The one that I showed you about that calculates the probability. So we're going to say define. I think that's how you spell Gaussian. Some people call this a probability density function, PDF, but you know, just to not throw in more terms out there, I'm just going to call it Gaussian, and that's it, right? So we have our three functions over here. So we're going to start defining these as well. All right, so what are some of the things that we need? So so before we get to predict, right, we don't have to get to predict and Gaussian until we get to train, right? So for train, we need to perform several steps, right? So we can get rid of this print here. Let me save this before I lose it. All right. So what are some of the things that we need? Train will get train will get X train, right? X train and Y train. So as we defined it in the previous video or lecture where we talked about, where we talked about the domain. Okay, so we have that there. Once we have this, we need the number of samples, right? That's usually good to know frequencies, so number of samples, and we need the number of features as well. If we try to think in terms of Iris, which has 150 samples, 4 features, 3 classes. That'll make things a little bit easier. So then we do n samples, n features. Okay, so that's our set of values. Then to get this, because this is a numpy array type, we can just do shape. All right, so if we do x shape, that returns 2 values, which are the number of samples and the number of features. Okay, we also probably want to know the classes, right? Which classes we have. So we have, for instance, we can call this list of classes, right? And this will be, if we're thinking of Iris, there's going to be, I'm going to write here, for Iris, there are 3 classes. So you get, let's say 0, 1, 2. So you get 2 classes there, 0, 1, and 2. And so to obtain those values, we can pretty simply do that by using numpy. So that's going to be np unique of y. And what this does is it's going to return, it's going to look, of y train, sorry. The y train. It's going to look at y train, all the labels, and it's going to find all the unique ones, right? Because you're going to have, out of 120 samples, you're going to have a lot of 1s, a lot of 2s, a lot of 0s. But it's only going to return 0, 1, and 2, because those are the 3 unique classes that you have. So this looks like an array or a list, okay? And then finally, another thing that we need is n classes, right? Which is the number of classes, which should be simply by doing the length of the list of classes, we will know, right? So we take list of classes, which is 0, 1, and 2. Then we take the length of it, and now we know n classes. So n classes here will be 3. And actually, let me say that over here. So I'm going to say here, n samples is 120, right? Because this is Iris. So remember, for this example assumes Iris, let's say. This example assumes Fisher's Iris, okay? So then it's going to have 120 samples by 4 features, okay? And the number of classes here, assuming Iris, would have, this is important to better understand the algorithm, this would have 3 classes. Make sense so far?
Yeah.
All right. So the next question that we need to figure out is, we need to remember, we need to look at, we know that we're going to be using, if I go back to the whiteboard, we know that we're going to be using this, the Gaussian function, right? But we also said that we're going to be using the probability. Remember, we need this term that you're seeing here, right? And that's based on the Gaussian now. And we also need this one, right? Now this one is not using the Gaussian, it's just a simple frequency. So we need to figure out then, number of samples, etc. Right? So these are the two that we're going to try to start to calculate the parameters that we need in order for us to have these values. Okay? So I'm going to go back to the Jupyter. Okay? So I'm back here at the Jupyter Notebook, and now I need to start thinking about how do I calculate these values. Okay? So to calculate these, let's just say I need to calculate, those parameters. So I need mean, the means basically. I need the variance for the Gaussian, and the prior probability, probability for the classes. If you remember, we had called the prior probability, so let's go back to the slides. That's why we kind of gave it a name so that we could identify these. If we go over here, you can see that here, right? The priori. We had called that the priori or the prior probability, and that's what I mean. This term, so for the Gaussian is this, right? For each, that we need given a document and a feature and a class, the likelihoods are the Gaussians, and then we need this, the priori, which is just for the classes, right? So for each class. So let me then go back to, okay. So, and the priori probability for the classes, okay? So we need to calculate those. So then, as it turns out, we need to create the following. So let me go back to the whiteboard here. All right, so you should be seeing the whiteboard. Okay, and we need to calculate basically the means, right? So for the means, we're gonna build a kind of a table. All right, so the table of the means is going to be n classes by n features. So we have n classes over here, and then we have n features over here. All right, so n classes and n features. N classes is going to be if we're thinking about iris, right, it's going to be 0, 1, and 2. Or Virginica, versicolor, what is it? Virginica, versicolor, setosa. Right, those are the three classes. So for each class, we need a row. And then for each of the classes now, we need to look at each of the individual features. So F1, F2, F3, F4. So we're going to look at feature 1 for class 1 and calculate the mean. Then we're going to look at feature 2 for class 0 and calculate its mean. Then we're going to look at the feature 3 just for class 0 and calculate its mean, and so on. All right, all the way. So let's say over here, we look at the class 2, setosa, and we look at the feature 3 for that class, and we calculate the mean of it. Do you see that? So we need to calculate these values because that's how we're going to be using them. And the same applies for the variance. So this is the mean. For the variance, we sort of need to do the same. We're going to calculate the number of classes, n classes, So it's going to be 0, 1, and 2. And then the features are going to be 4, right? For iris. So F1, F2, F3, F4. So for each one of these, we need to calculate again the variance. So given class 0, we need the variance for feature F1. And then, for class 0, feature F2, calculate the variance. And so on all the way to the end. For class 2, all the way to F4, we calculate the variance. All right, so we're going to need these tables so that we can later on do the calculations that we need for naive Bayes to work. Okay. The priors, if you remember, the priority just means we need the frequency for each. So the priority means that we just need the frequency for each class. Okay, so we just need the frequency for each class. Therefore, for this one, we just need a simple vector, right? So we will just need a simple vector of size and classes. So this will be of size and classes, given that we're just going to calculate the frequency, for class 0, for class 1, class 2. But, what we're going to have there is the frequencies themselves, right? So frequency, I should say, of 1, frequency of 2, frequency of 3. Do you guys see that? And so we're going to create those 3 tables or vectors, etc. So let me just kind of wrap up with this part today. But let me switch back to the Jupyter Notebook, and then we'll continue the algorithm on Wednesday. So here we can see that we want a mean. We want a mean, right? This is just to hold the data right now. So if you remember when we were doing the numpy examples, I did NP zeros, right? So this is an example of how you use it. So here I'm going to say NP zeros, and I want to create a table with using this tuple, which defines, okay, I want this to be n classes, comma, which I have right here, right? I have this, n classes by n features. I also have n features over there, so I can just say n features. And then I want to specify the kind of data that I'm going to store here. So I'm going to say D type will be np dot float 64. You see that? And that's the table that I just described before. And then I can do the same for the other one. You could call this means and variances. That's sometimes more helpful. Means. So here I could call this variances. All right, and it's going to be the same NP zeros. It is of size n classes by n features. It'll just have different data, and the data type can also be float 64. Right? So it can hold big floating point numbers. And then the last part is what we're calling the priority, right? So priority, that frequency value, and this is just going to be NP zeros without a tuple, just because it's just a vector of size 3. So we're going to say n classes. So it's going to hold 0, 1, and 2. Three frequencies, okay? 3 frequencies. And then the data type can also be of float 64, okay? So that's, believe it or not, this is not as complex as you might think. We just have like 3 main parts to finish up. And the PDF really, I mean, we could always honestly just use the built-in function. However, we might look at the actual equation. I'll figure it out. But we're going to stop here. So I'm just going to write a comment, stop here, so that I know where to pick up on Wednesday. Okay? So that's it for today. This is, let's call it the first part of the naive Bayes algorithm with Python and NumPy, and then we will finish this up on Wednesday, hopefully, and also wrap up the lecture on performance metrics. All right, guys, so let me save this. I'm not going to load this Jupyter yet, given that I'm not going to load it yet because, I don't want to give you the incomplete code, but I'll load it on Wednesday, okay? Now, what I do want to do is I'm going to go to the notepad, and I'm going to save the PDF. So I'll be loading this in a sec as well. All right, guys? So we'll stop here for today, and I will see you on Wednesday.